In this second video about the squeeze theorem, we'll talk about how we can use this theorem to solve problems that'll be given to you in your homework and on exams related to the squeeze theorem. We'll see how to identify these problems and how to approach them and know how to solve them. So let's start with the statement we had of the squeeze theorem from last time. All right, so there is our statement of the theorem. Now, how do we use this to help solve problems? Well, problems like this will generally be asked in the form find this limit or evaluate this limit. So you'll be given basically that expression there as part of the problem statement. As to find a certain limit, you'll be given find limit x goes to c f of x, which means in this problem what we know already is we know f and we know c. What we then have to do to solve the problem is find the rest of these bits. We have to find L, we have to find U, such that all of these conditions are met. To summarize, we're given f of x and c. We need to find U and L that meet the conditions of the theorem, and then we can apply the theorem to get our result. And that is the tricky part of this problem here, is figuring out how do I pick the appropriate functions U and L to make this whole theorem work together. We'll see a couple of examples on how you can think about this, but that's where we're headed. How do I pick U and L to make all of this work? Once we have them, apply the theorem, and we're good to go. So here's our first example, the same one we sort of talked about in the first video. So I want to use the squeeze theorem to compute the limit as x goes to 0 of x sine 1 over x. We'll jump back to the graph real quick to show you what we're looking at here, and it's that. The limit should be 0. So the picture tells us that's what we're looking at here. And we also saw in the first video that we can't use our normal multiplication rules to split up limits because this one limit does not exist, right? The limit as sine 1 over x, x goes to 0 doesn't exist. That's like taking the limit of sine as x goes to infinity, which just oscillates back and forth and doesn't have any limit that it converges to. So we can't do it this way. What else can we do? The answer is squeeze theorem. So to motivate this, we can't use our multiplication rules because that limit does not exist. And that's one of the examples we talked about earlier in this chapter about not existing by oscillation. That's what this function is right here. So we need to use the squeeze theorem. So what do we have to start with? We know, based on the problem statement here, that my function f of x should be x sine 1 over x, and my point c should be 0. Now to figure out, how can we find what these functions L and U should be that are going to set up our expression to satisfy the squeeze theorem? Well, one of the main ways you can start processing this is by thinking about what is the problem with this limit. And the problem with this limit is this sine 1 over x term. It doesn't exist as I go to 0. It's a problem. But it's not really too bad. What do we know about sine 1 over x? Well, it's not going to exist as we go to 0, but it's a sine function. And sine functions are always between minus 1 and 1. So we know that sine 1 over x is going to be no bigger than 1 and no smaller than minus 1. This middle part here is almost f. To get to f, I have to multiply it by x, but that's going to cause two different inequalities if x is positive or negative. So if x is positive, I can just multiply by x directly and get an inequality from that. But if x is negative, I reverse the inequality when I multiply by it. And I can flip the second one around just to make the directions match. Now let's take a look at this upper part of this function that is bigger than f of x, right? This middle bit is f of x. So what is the function that's bigger than f? Let's just take the bigger part of both inequalities here, meaning I want this part up here and this part up here, to give me that my function u should be this function. But what is that function? Well, that's just the absolute value of x. It is x if x is positive, and negative x if x is negative. That's the absolute value function. What do I then get for L of x? So what do I get for L of x? Let's just take the lower half of these two functions, namely this bit and this bit, to get negative x if x is positive, or x if x is negative, which is just the negative absolute value function. So what these two inequalities here show is that u is bigger than f for all x not 0, and L is less than f for all x not 0. That gives us the following, right? And that's a good start. If you want to do squeeze theorem, this is the setup that we need for limits going to 0. Now let's figure out these limits. I have to take each of the limits separately, and if they both go to the same value, I can then use squeeze theorem to get my answer. So let's start with L. I limit them going to 0 because that is the point that I care about. There's my function L. But we know what this is. This is an absolute value function. You could break it up into two sides if you wanted to, but this goes to 0. And the same goes for u of x, where that also goes to 0. So we have condition 1, the inequalities, and condition 2, the limiting being equal. That is enough to apply the squeeze theorem. So thus, by the squeeze theorem, we know that this limit must exist and be equal to 0 because both u and L limit it to 0. And there's our final answer, which is the answer we expected to see based on what we saw in the graph of this function. All right, so what is the process behind all of these problems? The idea of this and the hard part of it is always figuring out what are my functions L and U going to be. The rest of it's sort of given to you in the problem statement, right? You're given F and you're given C. The question is then, what are my L and U supposed to be? A general trick here, which is probably the way you want to approach these, is look for which part of this goes wrong, right? What part of this limit doesn't exist to make you be forced to use squeeze theorem? So in this last case, we had the sine of 1 over x term. In other problems, could be anything else, but what you're looking for is a limit that doesn't exist. Your goal then should be to take this bad part of the problem and try to bound it somehow and make it nicer, right? In this last case, we had sine 1 over x. We made that between minus 1 and 1 because that's what we had, right? Sine is bound between minus 1 and 1. Doesn't matter what you put in, you're getting a number between minus 1 and 1. So find some way to bound this guy or make it nicer, maybe trap it somehow, whatever you have to do to make it look a little bit nicer, and see where that gets you. Then you want to work this bound that you get into your original function and see if the functions that come out of that could be useful for the L and U. And here I will point out as well, absolute values are your friend. Why? Because they're always positive, or negative absolute value is always negative. And so you're always on the same side of 0, which means if you put that in anything else, you're always on the same side of your function. Keep that in mind when you're working these out. And then finally, you have to at least check the limit condition to make sure that L and U both limit to the same number at the point you care about, and then you're done. At that point, you're good to go. All right, let's check one more example of this and how this comes together, and then that'll wrap up this video. So this function looks complicated, but it's really not too much harder than what we just did. So use the squeeze theorem to evaluate the limit as x goes to pi over 2 of cosine x times sine of tangent of x. So first point, what's the problem here? The problem here is the second term, the sine of tan of x term. The issue here is that the limit as x goes to pi over 2 of tangent of x doesn't exist. On one side it goes to plus infinity, one side goes to minus infinity. So the combined limit there also doesn't exist. But thankfully we can use the same trick as before because this part is of the form sine of stuff. So that's always between minus 1 and 1 no matter what we do. As long as I don't plug in pi over 2, we're fine. And now I want to get this back to our original function. Now, one trick we can use to make this easier and simpler than the previous one we did, you could also apply this trick to the first example, is use absolute values. So what this tells me here is that the absolute value of sine of tangent of x is less than 1, which means I can multiply both sides by the absolute value of cosine x and then put the absolute value inside on the left. This tells me the following inequality, right? That's working absolute values, that's entirely fine. And now I can undo the absolute value inequality and make it back to a regular inequality again, giving me the plus and minus of the absolute values like we had for the minus absolute value of x and the absolute value of x in the first example. So this here is equivalent to this inequality here, which now gives me good candidates for my L and U functions. Because this guy here in the middle is the f that I care about. So I have the inequality condition satisfied for these functions L and U. Now let's check the limits. So for L, we get that function, and as x goes to pi over 2, cosine of pi over 2 is 0, so this is 0. And similarly for U, this is also 0. Thus, we get the answer we want using the squeeze theorem. These two numbers are the same, and the inequalities are satisfied. So, by the squeeze theorem, if the limit of x goes to pi over 2 of cosine of x, sine of tangent x is 0, which is our final answer there. That gives you two pretty straightforward examples as to how this problem works. The important thing to realize here is for both these problems, we took the sine of x, the trig function, and bound it between -1 and 1. This will work for both sine and cosine. So if you see those ones, you can look for those ones first to try to simplify out your problem. The next video will cover two more examples of using the squeeze theorem, but with functions that aren't trig. So we'll see other ways this can show up, of course, across problems, and work through those ones as well.